Good morning or afternoon or whatever it is. This is a rundown of the most missed questions from exam 2. I went through the item analysis and I pulled each question where fewer than 70% of the students got it correct. And so that's how this list got compiled. I'll warn you, they're probably not in the same order as they were on the test. But that's okay. You're grown-ups, you're intelligent people, you'll figure it out. This first one that I pulled says S and T are independent events. Probability of S is 0.66. Probability of S and T is 0.35. We need to find S given T. Well, when I go to my handy dandy formula chart, I immediately go to the independent events section because that's the first thing we were told about S and T. Now, what I have in all of these is A's and B's. So if that is a little bit confusing, you can totally rewrite the ones you're given in the problem in terms of A and B. So we could say A and B are independent events. Probability of A is 0.66. A and B is 0.35. Find the probability of A given B. That's a little easier because then you can go over to your formula chart and you can pull off the A given B part. And it tells me that the probability of A given B is equal to the probability of A. Well, the probability of A was 0.66. That's all you gotta do. Use the formula chart to help you get through these. Don't try to memorize it all, but also you don't have time during the test to necessarily go flipping through all of your notes. So getting familiar with what's on that chart is pretty crucial to your success. Now we have a contingency table. We have students who completed the homework, did not complete the homework, passed the course, and did not pass the course. Right away, I notice that my entire sample space is 51 students. So we want to find the probability that the student passed the course or completed the homework. Now, anytime we have an or, we have to be careful to not double count. What do you mean by don't double count, Miss Graham? Well, I am so glad you asked. I'm going to start out with all of the students who passed the course. So I have 30 total that passed the course. Then I'm going to go look at the ones who completed the homework. That's the section. And I have 23 plus 6 equals 29, and they completed homework. Right here is what we mean when we talk about double counting things. That 23 got counted in the 30 and it got counted in the 29. So we've counted that group of 23 people 2 times. We only want to count it once. So when I look at the probability of they passed or completed the homework, I want to add the total that passed plus the total who completed. Miss Graham, you said don't double count. I'm fixing to fix it. I'm going to subtract the ones that got double counted. And then all of that gets divided by our total sample space. I'm going to pull out my calculator, so give me just a second. I love you guys enough to not do this in my head. 30 plus 29 minus 23 is 36. Divided by a total of 51. And we want the decimal to 4 decimal places. So that would be 0.7059. So don't double count. Okay, now we have the proverbial deck of cards. It seems like this is a ridiculously common statistics or probability problem. The only thing that's missing from the picture of the deck of cards is the queen and the king column. I just didn't have big enough space when I screenshotted them, but we know they're there. We are going to draw one card. What is the probability of selecting a spade or a 10? So I'm going to follow the same idea from the contingency table. I am going to highlight all of my spades in pink. And that is not a high quality highlighting job, but you get what you pay for. Remember, we have a queen and a king out there. Now I'm going to highlight all my 10s. Let's make those blue. Do you see it? I'm pretty sure I heard you say you saw it. Here's what we've got. We have 13 spades. That one's in a windstorm. And we have 4 10s. But this 10 right here, this 10 of spades got counted twice, so we have to subtract it. So the probability of a non-crooked spade, it's still crooked, is the total spades plus the total 10s minus the number of cards that gets double counted out of 52 total. So 13 plus 4 minus 1 all over 52. They want to reduce fractions, so I'm going to use Desmos to do that. I get 4 out of 13. Now we're picking 4 cards. And when I have students who come in my office who struggle with problems like this, we write it out pretty literally. We're going to pick 4 cards, and we are not going to replace it each time we draw it. So I'm going to draw one and keep it. And then draw another one. And then draw another one. And then draw another one. Now the first time, I'm going to move that down a little bit. Oh, dang it. I guess I'm not going to move it down. I want a queen each time. How do I know? Because I read the rest of it. That means the first time I draw, I have 52 cards to choose from. And I have 4 queens in the deck. But when I pull it out, I'm not going to put it back. I'm going to keep it. So that means I have 51 cards left, and there are only 3 queens left. So then we keep the next one, or we keep that one. We only have 50 cards left and 2 queens. And then we have 49 cards and 1 queen. And we multiply. So I'll do 4 over 52 times 3 over 51 times 2 over 50 times 1 over 49. And I get an answer that is very delightful. I get an answer that says 3.6938 times 10 to the negative 6th power. Now, I realize it does say to leave your answer as a fraction. I want to make sure you understand what's happening here in the event you get asked to leave it as a decimal. So just hold your horses. This negative 6 means I want to move the decimal 6 places to the left. 1, 2, 3, 4, 5, 6. Miss Graham, what do I do with all of those empty spaces? Well, you can't leave them empty, so you add zeros to fill up all the holes. So 3.6938 times 10 to the negative 6th. In standard form, instead of scientific notation, looks like that, which is essentially 0. Thankfully, we do have the fraction button in Desmos, and it converts our fraction, or our decimal, to 1 over 270,725. You're probably more likely to get struck by lightning. Hold on. Oh, no, I was wrong. The probability of being struck by lightning in any given year is less than 1 in a million. So this is actually significantly higher than that. We have another contingency table. The first thing I like to do if it's not given to me is add a totals column. And then a total down here. So 44 and 41 is 85. 10 and 5 is 15. If I add the males, I get 51. If I add the females, I get 49. Both directions, I get a sum of 100. That confirms what they told us. We have a total sample of 100 individuals. We want the probability of female and left-handed. So when I go to my contingency table, females are that row. Left-handed is that column. Now remember, and means we want both things at the same time. So we want the females that are left-handed. That happens in our double shaded region right here. So the probability of being female and left-handed is 5 out of a total of 100 people. Does it say how to leave it. It doesn't say, at least on the part that I screenshotted. So if I reduce this by 5, I would get 1/20. Female or left-handed, when it's an or, we take out the double counted parts. The double counted parts happens to be that 5 that we used for the and. So I need total females, total left-handed, minus the ones that were both, out of the total sample size. So essentially this is 49 plus 10, that's 59/100. And I believe that's already reduced. We're going to double check just in case. Yeah. So our probability is 59/100. If you want the decimal equivalents for these, this would be 0.05 and this would be 0.59. Okay, American Airlines flights are on time 50% of the time. Suppose 8 flights are randomly selected and the number of on-time flights is recorded. So this turns out to be a binomial distribution. We've got our random variable, a binomial distribution with n is our sample size and p is the probability of success. It's binomial because we have a fixed number of trials, random selections, and we only have 2 options. Your flight's either on time or it's not. This tells me that I need StatCrunch. I don't think I already have it open. I do, but it might kick me out. We'll see what happens. So I'm going to go to Stat, Calculators, Binomial. Now, my n is 8. My p is 0.5, that's okay. Now I need to decide what my bottom line is going to say. The probability that at least 3, at least means greater than or equal to 3. So over here in StatCrunch, I'm going to change my inequality symbol to greater than or equal to. I'm going to put in a 3 and compute. So the probability that at least 3 flights are on time. We don't have rounding instructions, so I will use 4. Eight, 5, 5, 5. Yep. So now I want the probability that at most 2. At most is less than or equal to 2. Make sure you change the inequality sign. So the probability that at most 2 flights are on time is that guy right there. Now the probability that exactly 3, that means equals 3. So I'm going to change the inequality symbol. I'm going to get rid of the 2 and make it a 3. to 4 decimal places would be 0.2188. We have another binomial. The success rate of corneal transplant surgery is 87%. That means our P is 0.87. That's the probability of success. The surgeon performed 7 patients. We have an N of 7. That's a fixed number of trials. The surgery is either successful or it's not. So we have a binomial distribution again. Remember, we use B for binomial. N comes first, and then P. I'm going to alter my StatCrunch. I have an N of 7. P is 0.87. I'm going to clear out what I had in the one from before. Now this says exactly 6 surgeries. So I want the probability that X is equal to 6. I still have my equal sign in there from the previous problem, so I need a 6, and I'm going to compute. So the probability that exactly 6 surgeries are successful is 0.3946. Why did I do 4 decimal places? Oh, look, it does have directions that says 4 decimal places. That's why. Less than 3 surgeries are successful. Less than looks like this, so we want the probability that X is less than 3. So I'm going to change my inequality. I'm going to plug in a 3 and click compute. This is 1, 2, 3 zeros and a 6. Which is not a very mathematical way to say that, but that's how my brain interprets it. At least 2 surgeries. That's greater than or equal to 2. So the probability that at least 2 surgeries are successful. Now, if I round this number to 4 decimal places, that's the 9 right there. So I look at the 6. 6 is bigger than 1, so I bump the 9 up to 10. But that bumps this guy to 10, which bumps this guy to 10, which bumps this guy to 10, which makes this approximately 1.0000. I would include the zeros. You may not have to, just in case the zeros might be a good idea because that indicates we rounded, but it may not be necessary. That's one of those that on the test, if you put 1 and it wanted 1.0000, I'll fix it. It looks like, let's see, it has been estimated that about 27% of residents in Ventura County have adequate earthquake supplies. Suppose you randomly survey 23 residents in the county. Okay. Well, I see a fixed number of trials. I don't know why I changed colors. I see only 2 options. You are either prepared or you're not. And I see a probability of success of 0.27. So that means we have a binomial distribution with an N of 23 and a P of 0.27. So we're doing the same thing. I'm going to change my numbers. What is the probability that it's exactly 9? So X equals 9. All StatCrunch. 4 decimal places. Yes. What is the probability that at least 9? At least, oh, stop it, is greater than or equal to 9. So the probability that at least 9 residents who have adequate supplies are in the survey. At most 9 would mean less than or equal to 9. So we change the inequality symbol one more time. 0.9344. Now all of a sudden this one is different. They throw in a between. We want the probability that between 5 and 10 inclusive have adequate earthquake supplies. So this time I need to go up to the top of my StatCrunch screen and click on between. I don't know why there's a 3 and 6, but I'm going to put in a 5 and a 10. And that probability is 0.7586. So that's how that probability distribution works, or binomial distribution. And what do we have here? 70% of people order water. A random sample of 25 people is taken, and each person is asked if they order water. Well, you either order water or you don't. We have a fixed number of trials. We have 27 trials, or 25 trials. And we have a 70% probability of success. My brain shorted out there for a second. So we need an expected value. Well, because I have my handy dandy formula chart with me, or at least I will here in a minute when I pull it up on Google Drive. I know that the mean, or the expected value, is number of trials times the probability of success. So I am going to multiply 25 times 0.7. And again, because I love you, I am not going to do that in my head. So I have an expected value of 17.5. What is the standard deviation? To 3 decimal places. Well, again, I'm going to refer back to my handy dandy formula chart. And it tells me that the standard deviation is the square root of NPQ. But wait a minute. I've got the N and the P totally under control. This pesky Q is the problem. But also on my handy dandy formula chart is a note that says PS. It doesn't actually say that, but Q is 1 minus P. Well, that's awesome. This time I'm going to pull up Desmos on my iPad so you can see me plug it in. So give me a second. So I'm going to do the square root of 25. P was 0.7. And I need 1 minus 0.7. Miss Graham, couldn't you just do the 1 minus 0.7 and get the answer and then type it in? You absolutely could. But I also wanted you to see that you don't have to. You can plug it in as 1 minus P, and it comes out just fine. This tells me that the standard deviation to 3 decimal places is 2.291. Now, we want to know what an unusual number of people would be to order water. Well, on your formula chart, we have the range rule of thumb to find unusual values. It says values that are low are less than or equal to mu minus 2 standard deviations. Well, it just so happens we have mu. And we have a standard deviation. And we have Desmos to do the hard part. So anything less than 12.918, it says round to the nearest whole number. So anything less than 13 would be considered unusually low. My formula chart also says it's unusually high if it's greater than or equal to mu plus 2 sigma. Well, the good news is I still have these. These are the same ones as before. I just change it to a plus sign instead of a subtraction symbol. Rounded to the nearest whole number is 22. That is the end for exam 2. I'll get exam 3 posted soon. If you have further questions about your exam specifically, feel free to come in and see me, send me a Canvas message. We can Zoom, we can get together on Upswing. You have lots of options to get your questions answered. See you later.